So in the last lecture, I would like to do the following two things. Number one, discuss the boundary regularity of quadrature domains in more detail. So far we already know that this must be a real algebraic set. And yesterday, by using the Alexander-Becker Theorem, the polynomial P which describes your domain, the boundary of the domain, must have a very special form. Namely, the leading terms must be x squared plus y squared to a certain power. But we'd like to investigate that in more detail. This is the second part is to show that quadrature domains are dense in the class of smoothly bounded domains. In C. Okay, so the first one is a theorem of Sakai, and the density theorem was first proved by Gustafsson and more recently by Bell. So we'll be discussing Bell's approach. And the advantage of this is that it brings into play the Bergman kernel in this business here. So Sakai considered the following situation here, problem. So suppose I look at, so this is a purely local problem. So I have the ball, the disk of radius 1 in C, and there is a certain subdomain of this. I'm not drawing the picture because, well, let me draw something anyway. This is too simple. So let D be an arbitrary open set you don't want this to be connected. An arbitrary open set such that the boundary of this domain contains the origin and the origin is not an isolated point in the boundary. Okay, so there's a whole bunch of points. The boundary is big. Also, assume that there is a function S which is continuous on D union the boundary, so D closure. S is holomorphic on the domain D, and S of Z equals Z bar on the boundary. The problem is to describe describe the boundary of such a domain. So if you think about this in connection with what we have discussed about quadrature domains, you have exactly this situation but it's a global thing. S is defined everywhere in your domain, it equals Z bar, and therefore there is algebraicity and so on. So this is a very local version of that problem. So Sakai proved a very beautiful theorem which completely describes all possible domains and their boundaries with this data theorem. This is from the early 90s, and the paper of Aronow and Shapiro that we have been referring to so far is from the mid 70s. So one of the following occurs. So number one, D is simply connected and the boundary is a smooth real analytic arc. This is what D is. Number two, DE consists of two simply connected domains. So there are two pieces, say D plus and D minus, and the boundaries of D plus and D minus are distinct smooth real analytic arcs that are tangent to each other at the origin. This is the other possibility. And number three, D is simply connected and the boundary is smooth real analytic away from 0. There is a singularity at 0. And 0 is an inward cusp. So your domain looks like this. And there is a degenerate case also. The degenerate case is basically you look at this situation and from your arc you delete a bunch of countably many points. D is the resulting domain there. Okay, so remove a bunch of points from case 1, from the boundary in case 1. So Sakai's theorem actually completely classifies the possible singularities of the boundary of a quadrature domain. This is clearly seen in the case of the disk, or whatever it is. Locally the boundary looks like that. This and this, especially here, they are also realized. There are concrete examples of quadrature domains whose boundaries locally look like this. So when does this kind of a situation occur? I think in the second or third lecture, we looked at this example of a map z going to z plus cz squared for c small. Yeah? And by the theorem of Aronoff and Shapiro, this is the image of the unit disk under this map is a quadrature domain. Right? So if you plot this, you get a bean-shaped region like this. So this is your inward pointing cusp. And so this actually occurs. And this also happens. So there is a cubic polynomial, cubic holomorphic P. In fact, there are plenty. Cubic polynomial such that the image of the unit disk under this is of the form, looks like this. So there is an outer boundary here. These two lips together, and there are two inward cusps. This is your domain. So there you have it. Near this, you have two pieces, and you have the inner cusps here. So all these happen, and these are the only possibilities. One of the interesting things that this is saying is that your quadrature domain can never have an outward pointing cusp. That's not allowed. And Sakai's theorem also tells you how to uniformize such a region here. Okay? So this will turn out to be, the Riemann map will turn out to be, of course, a holomorphic map. The map will extend continuously to the boundary, and it will have the second derivative vanishing here. That's like an algorithm to generate these examples. Yeah. The second derivative vanishes. Okay. So one way to view this problem is to think of this as a free boundary problem. Okay, so you have some analytic data that is imposed on your domain, and you're asking, describe the domain D, subject to this datum. So Sakai's proof is, if you read the paper, and I'll list all the references today at the end. You read the paper, it's a very beautifully written paper. All the details that one would like to see are there. But very early on, he introduces a new function. He says our study will be focused on the function which is z times s of z. And all the analysis is done with this function, and all these three consequences are consequences of the properties of these functions, of this function. Now this is where I sort of personally got stuck, and I was not sure what really is happening, what is the motivation behind considering this very special function, z times s of z. But then it turns out that, again, if we use the Alexander-Becker framework that we discussed yesterday, z times s of z has a very natural appearance. So I'd like to explain that first. So we just comment by saying that Sakai's proof studies the function z times s of z. You will of course notice that on the boundary this function is zz bar, which is real valued. Okay? So Sakai makes very powerful use of this, a very simple observation here. But where does this come from? Why is this relevant? That was not clear to me. So let's go back to the Alexander-Becker theorem. So what does this theorem say? It says that if you have an analytic variety, dimension 1, in a domain omega minus say Rn, omega is in Cn now, and suppose A is symmetric with respect to Rn. So there's a standard notion of reflection across Rn, Z1, Z to Zn, going to Z1 bar, Z2 bar, Zn bar. So you have this natural involution. So this being symmetric means sigma of A is A, where sigma of the Zi's are the conjugates. Then a closure is an analytic set in omega. Okay, so yesterday we briefly discussed this because Rn happens to be totally real and your analytic set has all sorts of complex tangents. What happens when you get very, very close to Rn? The limit of these complex lines is again going to be complex. But the limit cannot be contained in Rn because there are no complex tangencies there. So in some sense, this is saying that there can be no wild oscillations near Rn. A is very well behaved near a totally real set. It sort of goes past it. That was the thing. Now, one very interesting part of the proof of this theorem is to construct a proper projection from A to a certain open set in C. Okay? So how do you study the local structure of varieties? Well, you pick a point on your variety and you try to find a direction which is orthogonal to B in some sense, so that you can project along it and locally get a proper projection. If you do this, then your variety can be expressed as the zero set of certain Weierstrass polynomials. This is exactly the proof of the Weierstrass preparation theorem. Yeah? Now, you want to understand A near Rn, near a point in Rn. A priori, we don't know that A is analytic near Rn. So I have to come up with a suitable projection which will exhibit A as a branched covering. This is where the insight afforded by Alexander and Becker comes into the picture. So they say, consider the following quadratic map. Let's give it some name. Let's call this F. Let's look at the zero set of F. Of course, contains the origin. But if you look at the intersection of the zero set with Rn, so what are all the real points on this variety here? The sum of squares must be 0. Exactly 1 point. So now the proof goes as follows. So here's your picture. So maybe say here is Rn, here is I times Rn. Maybe here is the zero set of F, intersects Rn only at 0. And get a different color. And maybe, and A is sort of all over the place here. Okay. So what can happen? Well, suppose one of the irreducible components of A is contained inside F inverse of 0. Look at that reducible component. What is its boundary on Rn? Its boundary consists of only 1 point. because that's our assumption. A is analytic everywhere except Rn. And if you happen to be in the green variety, the only boundary point that you see is 0 because of this observation. So for that irreducible component, 0 is a removable singularity because points are too thin. So we've taken care of those components. So we only need to focus on those components which are not contained in the green variety here. So take one of these components and look at the intersection with this green variety here. It's not properly contained. So what can the intersection be? The intersection has to contain at most countably many points, nothing more. And therefore, if you were to have only countably many points, F restricted to this orange variety is going to give you a proper map, because the preimage of 0 is not a continuum, there are gaps. So I can choose a suitable set of neighborhoods that avoids the point of intersections to get a proper map onto C. So this is where the theorem starts. So take an irreducible component of A not contained in F inverse 0. Then F rest, so call this component, I'll give it the same name. Say A itself. So this is proper. So roughly that's the idea. Okay, and then the proof goes to claim the following. So here is let's draw some A now. The stuff in blue is Rn. This is A, and this is my sum of squares projection here. So I'm in C. 0 goes to 0, and what is the image of Rn under this map F of Rn? If I take real points, this is going to be bigger than or equal to 0. So which means that F takes values in this disk apart from the positive x-axis here. And then the theorem goes on to say that if you remove this, that means you're removing Rn upstairs, F becomes a proper projection here, and the orange stuff can be thought of as a branched covering over the slit unit disk. That's the idea. Okay, so you write down the symmetric polynomials, and there is an argument which shows that since A is symmetric, you can reflect this and form the symmetric polynomials, and that collection is going to actually extend to the entire disk. Okay, so the prototype example to keep in mind is the graph of the square root function. So you have two branches, plus square root z, minus square root z. Both of them are defined unambiguously on the disk minus the positive interval. And how do you glue these things together? You glue them together after you've completed one circuit. That's exactly what is happening here. So the local model for the singularities of such an A is given by the square root function. Okay, so this is roughly the Alexander-Becker theorem. And what is interesting is this map here. Very natural, very beautiful insight. So it turns out that this plays a very crucial role. Okay. All right. Just write down a bunch of steps that go into an alternate proof of Sakai's theorem using the Alexander-Becker approach. Step 1, and this is perhaps the most important step. So the limit of S of z divided by z is equal to 1 as you approach 0, staying within the domain D. Uh, Step 2. Well, before we get to step 2, so why is this important? Why is this important? So yesterday I said, well, let's not work with the domain, let's lift it, let's work with the graph. So look at the graph of S. ZD. So this is an analytic variety in the bidisk minus M. M, remember, was the totally real manifold, which we defined last time. W equals Z bar, right? Because S is equal to Z bar on the boundary, this is a variety in the complement. Totally real. Okay. So I'm going to the origin here. Yes. No, I mean you could sort of approach along different lines. Yeah. So that's the problem. Yeah. But yeah, that's a nice observation, because if I take any other boundary point apart from 0, this limit is equal to 1. Any other point. And because S is continuous on the closure, I know that this is going to be no bigger than C divided by mod Z near the origin. Yes. So S divided by Z is now a holomorphic function with this growth near the boundary at a certain point. Everywhere else it's equal to 1 on the boundary. So by a version of Ragman-Lindelof, it's an old theorem of Fuchs, this allows you to conclude that the lim sup of S of Z by Z is at most 1. Theorem of Fuchs, Ragman-Lindelof. And the nice thing about this is S divided by Z is sort of like the slope of this graph, y divided by x. And this is saying that this variety cannot be vertical at all. It must have bounded slope, bounded by 1. So you cannot have components of A which are vertical with respect to this projection. Bounded slope. No vertical components. Okay? But now let's do the same trick as yesterday. Here is my graph of S, the orange set. It may not be symmetric about Rn, but I can symmetrize it. So look at A union sigma of A, and that is invariant under the thing. Rn is the only obstruction. A union sigma A closure is an analytic set. Yeah? Again, please keep the prototype of plus square root Z and minus square root Z in mind. Okay, that's the thing. So the picture now is here is the graph of S. And here is its reflection. This is Rn graph S conjugate. Okay? So this is a removable singularity. Now you take a point on Rn, say the origin, and try to understand what the tangent cone is going to be to this variety. You are in dimension 1. So your tangent cone is going to consist of finitely many complex lines. Standard theorem. So there's going to be a bunch of complex lines like this. Complex lines in the tangent cone to this variety. So, should I say this? V is 0. So V is the graph of S union graph of S conjugate. Okay. So there are finitely many lines in the tangent cone. And now the interesting thing is to understand what the intersection of this complex lines will be with Rn. So there are only two possibilities. Your complex line intersects Rn exactly at 0, a single point, or it intersects in a real line. As a little bit of work will tell you that none of the complex lines in the tangent cone can intersect Rn in exactly one point. Because if it were to intersect in one point, what does that mean? So I take one of these complex lines, say the orange line. Corresponding to this, there is a unique irreducible component. Where does this complex line meet Rn? Exactly at 0. So the irreducible component is also going to meet exactly at 0, because the difference between them is of order 1. Right? And if it meets precisely at one point, show that this hypothesis is going to get violated. Because then 0 will be the only boundary point, which is not the case here. So any complex line in the tangent cone at 0 must intersect Rn, a real line. So let's slide this down. So CV0 consists of what are lines, i.e. They intersect Rn in a real line. Okay. And once you have this, the observation is the following. So observe. Okay, so I'm going to just work in 2 dimensions. So n is 2 sum of squares. Right. Little q as z squared plus w squared. And T, remember, was this map which takes M, that totally real manifold, and brings it to R2. So T as before, T of M is R2. So check that Q restricted to the tangent cone, which is semi-real lines, is equal to T restricted to any of the semi-real lines. Okay. So remember what this was? T was actually a C-linear map. It's just a 2 by 2 matrix, linear terms. But when you restrict the sum of squares or this C-linear map to any of the semi-real lines, you get the same function. This is a computation, not to be. Okay? Therefore, the expectation is, because your variety is very close to its tangent cone, Q and T will be approximately same, restricted to your variety also. Therefore, other thing to check is that the limit as ZW goes to 0, 0, this is a boundary point of the graph. Okay. Little q of ZW divided by mod TZW. Oh, sorry, this is T squared here, by the way. Okay, T squared. This is what? Modulus of T squared. And it turns out that little q and capital T can be actually described, because what is W after all? W is going to be S of Z if you're on the variety. So this is like Z squared plus S squared. You take the square root of that. Then you can write down what T is using that 2 by 2 matrix from last time. All in all, this expression turns out to be 2 times Z times S of Z divided by mod Z squared plus mod S squared. If the limit of this happens to be 1, it follows that the limit of S of Z divided by Z is equal to 1. It's like 2ab divided by a squared. Kind of thing. Okay. So this is where the information is that the graph cannot be vertical, bounded slope. And the other piece of information is tell you about the sum of squares. Turns out that if you look at Q, composed with T. So T first of all is going to bring M into R2, where you can apply Alexander-Becker, which means you have the sum of squares function here. So I'm pulling the sum of squares back by capital T. That's exactly what I'm trying to do here. Little q composed with T. This turns out to be exactly S of Z. So I'm restricting this to the variety. Restrict this. This turns out to be Z times S of Z, which is what Sakai considered. So what is the moral of all this? On Rn, you have the standard conjugation where you can apply this theorem. Yeah, so I'm pulling this picture back by means of this linear map, capital T. The sum of squares becomes the product, Z times S of Z. And as a byproduct, we are also able to show that the graph has no vertical lines present in there. So now we're all set. So this is sort of like the initial preparation for applying this theorem here. So step 2 Step 2 is to show that the multiplicity. So now the picture is then you have Q composed with capital T to C, right? The pullback, the sum of squares to be here. Step 2. So this is a branched cover over the disk minus the positive interval, and more importantly, each fiber has at most 2 points. So this is either single sheeted or it has 2 sheets. And the way to prove that is one has to sort of apply the principle on this variety to the function S times Z. So use argument principle. So end game is, there are 2 cases. If the multiplicity is 1, you are exactly in case 1 of Sakai's theorem. If the multiplicity happens to be 2, case 1 is yes. Yeah, case 2 sort of splits further. You have this or this. Okay, so there's a fair bit of sort of local analytic analysis of this kind, but this is the crux of the argument. Okay. Now, in the remaining time, I would like to introduce some work done by Steve Bell, this class of domains here. Let's discuss the density theorem. Bell. So Bell has introduced techniques from the Bergman kernel to address quadrature domains in a very, very nice manner. We will look at quadrature domain now for the class H2 omega. So square integrable holomorphic functions. I've just changed my test class a bit now because you need inner products and so on. So same definition as before. Integral of f is the sum Cjk f to the k qj. Okay, qi's are the nodes. So use the Bergman kernel for omega. So let me just write down some of his observations on this very nice paper that he has written. So first of all, observe, K has this Bergman kernel has reproducing property. So if you act against holomorphic functions, you get evaluation and so on. And because of the reproducing property, integrating holomorphic function against powers of K will give you so many derivatives. That's the idea. So because you have derivatives here, we'd like to interpret this as the integral of f times a certain power of k. I get this. Right. So let me write down the left-hand side here as the inner product of f with 1. And on the right-hand side, you have the sum, the inner product of rather f with a certain combination of functions that look like this. Derivatives. Sorry, not powers. I said powers, mistaking this with derivatives. So this is the, thanks Zeta. So I differentiate only with respect to the holomorphic variable here. Right? So this is what I get. And this is true for all f in H2. And therefore the constant function 1 can be expressed as a Bergman curve, some of its derivatives evaluated at the nodes. So we define Bergman span of a domain omega. So this is the collection of the C-linear span of power like this, derivatives. So fix the conjugate holomorphic variable, allow the first one to vary and take powers, take combinations of these. This is the Bergman span. So this is telling you that if you are a quadrature domain, then the constant function 1 is in the Bergman span, actually belongs to it. And starting with this, you can retrace your steps and conclude that 1 is in the Bergman span if and only if you are a quadrature domain. Omega QD if and only if constant function 1 belongs to the Bergman span. That's the first observation. Second observation, so suppose that omega 1 and omega 2 are bounded domains in C, and F is a biholomorphism between them. Then omega 2 is a quadrature domain if and only if the derivative of the biholomorphic map F prime belongs to the Bergman span. There are no hypotheses on the boundaries, just this fact here. This is expected because think of F as a change of variables here. If you happen to have omega 2 to be a quadrature domain, then you can play around with the inner product, use the change of variables formula. The change of variables is going to involve F prime, and using all that, turns out that F prime must belong to the Bergman span. And this is coming because of this interpretation. And the quadrature identity involves powers of K. So that's
follow from the transformation law.
Transformation law.
No.
Times F prime, yeah. So that F prime is there, yeah. And the third ingredient is that if omega is smoothly bounded, then A infinity omega. So these are all the smooth functions up to the closure which are holomorphic. Then this class is okay, sorry. Then the Bergman span is dense. Bergman span is dense in A infinity omega. Any function in A infinity can be approximated by the Bergman kernel and its derivatives. Because after all, A infinity and A minus infinity, they are sort of mutually dual. And if this were to be false, if the statement were to be false, there would exist an element which is orthogonal to all derivatives of A. But then integrating against derivatives of K gives you all the powers of the function. So there will be a point where this function sort of vanishes. All derivatives of this function is 0. So this is so use duality of A infinity and A minus infinity. That's roughly the idea. So final conclusion using these three ingredients is that theorem, Bell on my chalk. Let omega be smoothly bounded, then in an epsilon neighborhood of the C infinity topology near epsilon neighborhood of C infinity in around omega, there are quadrature domains. So just perturb your boundary a little bit, you're sure to find a quadrature domain. Okay, so what is the idea here? Let's use step number 2. So I start with omega, which is an arbitrary smoothly bounded domain. I want to come up with an F which is close to the identity, because I want it to be close to omega, such that the image of this map is going to be a quadrature domain. And this happens if and only if I can arrange for the derivative of this to belong to the Bergman span of omega 1. Huh? So that's the crux of the problem. So I have to find an F close to the identity whose derivative belongs to the Bergman span. So I start with any function. So take so take the constant function 1. Constant function 1. Because you are smoothly bounded, 1 belongs to the Bergman span because of this property here. Okay, that's not good enough. I want to belong to the Bergman span completely. So I have to sort of correct this somehow. Correcting this means I have to perturb it, and I would then have to integrate this resulting function, because after all, I want f prime to be 1, it's close to the identity. So I want to perturb 1 and then integrate that. But your domain D might have holes in it. And integrating a random function is going to give you non-trivial periods around these things. So when I integrate this, I may not get a well-defined holomorphic function. So there is a correction to be done. So that additional correction means I have to eliminate all the periods around these things. So, so one, perturb and integrate. This is my recipe for my holomorphism F. To get F. This will be the derivative, in fact. F prime will be 1 plus something. So F should be like Z somehow. Okay, but the problem is of periods. 0 periods. And for that, there is this linearity argument. So, again, a very nice observation. So there are n minus 1 points. So n is the connectivity of your domain. So one outer boundary and n minus 1 inner boundaries. So there are n minus 1 points in my domain omega. N is the connectivity such that if you look at the following matrix M, say, and the ijth entry of M is the period of the Bergman kernel function Zaj along gamma k. So this is the jk entry. So what you do is, how do you do this perturbation? Well, you want to perturb in such a way that you eliminate all the periods. So the consideration is, you look at this. So look at 1 minus a certain linear combination of k, z, a, j, where aj's are these points. What the coefficients are, we don't know at the moment. But I want this new function to have 0 periods. So the integral around each of the gamma j's must be 0. So this is a system of equations. And the coefficient matrix is invertible. And therefore you know what these coefficients are. And you can control them because after all you just want to perturb slightly. So if your perturbation is slight here, the coefficients will be very small. Okay? So this is going to be your function now, which is going to belong to the Bergman span. Okay? So a little bit of work there. And then this is like f prime. And then there are no periods around any of these, so I can integrate. So f is z minus a very small perturbation. So, and because you're close to the identity everywhere and so on, so all these things can be done up to the boundary because your boundary is smooth. So f is injective everywhere in the closure. This theorem applies. So this is the density argument. So the original proof of this was due to Gustafsson, who used different arguments. This I think is very pleasant and brings into play a different viewpoint. So using this approach again, Steve Bell has been able to sort of, recover many of the theorems which people like Gustafsson and others have proved using different means. So it's quite pleasant, and I will just conclude by saying that the situation in higher dimensions is completely unknown. You have various definitions of what a quadrature domain should be, and the only theorem which Pranav disappeared. So which Pranav taught me was that there's a density theorem in higher dimensions also. And to give you an example of this, you take the ball in Cn minus 1 ball and take a cross product with a planar domain, smooth domain. So this is a domain with non-trivial topology. Look at a C infinity neighborhood of this boundary, of this domain. There are quadrature domains close by. And you can replace the ball with something more exotic also. Hypothesis will be true. So I think he's going to give a talk on his work, so I'll stop here. I'll also, in case people are interested, I'll just list some references. Not a particularly well-known or popular book, but I think it's such a marvelous bunch of ideas that he's put in there. And all these papers, especially the first two, for example, I think they are so beautiful to read. In case people are interested, please do spend some time. Gustafsson, of course, has made many contributions in this area, trying to understand the finer structure and so on. I should also mention Puttinger here for connections to operator theory. Yeah, and like as I said, the higher dimensional situation is completely open. I think it's a subject quite worthy of study. Okay, so I think I'll stop here. I have nothing more to say. Thank you.
Thanks, for the wonderful lecture.